Hello everyone, I would like to start today's lecture about discussing the MIPS data path. We're going to discuss the single cycle. This means one instruction will take just one cycle. So this is just a basic understanding of the data path. To understand more later on pipelining and other advanced architecture of the MIPS processor. So of course we are discussing a 32-bit processor. Alright, so if I want to describe the operations of any MIPS processor or any processor, we have certain stages that the instruction passes through until perfect execution. So first step, I would like to fetch the instruction. So what do we mean by fetching the instruction? Is actually taking the instruction out of program memory. So usually we have a program memory. Okay, so we have the instruction here, let's say it's add, and we have another instruction, let's say sub. I'm not gonna put the parameters here. So as we said, the instructions are 32 bits. So this means the instruction will be 32 bits, and of course this is byte address. We have 0, 4, 8 and so forth, and here we have a 32-bit address. So the first part is just taking out the instructions. So this means we need some sort of a counter which counts 0, 4, 8. And this is called the program counter. So if I want to explain more what do I mean by fetching each instruction, so this means, so I draw a clock cycle. So we have add taking place in one cycle, and of course sub will be taking place in another cycle. So this is cycle 1, this is cycle 2. This is the rising edge. Okay, so the counter, the program counter PC should be here 0, and then before actually reaching this sub it should be 4, so that at the next cycle the PC is already pointing to the next instruction. So the first, we already started with 0, 0 is fetched. Then somewhere between 1 and 2 we increase PC by 4. So this can be drawn very easily and designed very easy. So this is the program memory, as we said, and we have the PC is just a 32-bit register. So we have something like this. So this is the PC. This is the 32 bits. So here we start by 0x. So this is the first. And now after the execution of the first instruction, we need to add 4 to it. So the way we do it is actually, I'm going to do it in a different color. We will have something like an adder that adds to the PC 4 and stores it back. Okay, so this is 4. Remember, this is all 32 bits. So if we take a look, and of course PC is clocked. This is the clock. So at the first edge, if I want to trace it, at the first edge PC is 0. Now we have add here, so add, this is an instruction register, so if here we had add, let's say $S0, $S1, $S2. Okay, so the first what we mean by fetching is actually taking out add outside the program memory. But when we take it out, we add 4, so that the next time, so this will be 4, this will be here 4, so, and PC was equal to 0. So when we have the next clock cycle, 4 will go into, and the next instruction sub will be fetched also. So this is 1 happening at the first cycle, this is 2 happening at the second cycle, and the PC, I can define it as a register holding the address of the next instruction to be executed. So the PC holds 4, so that the next time we're gonna fetch sub, it's already ready on the next clock cycle. Now the second part of the MIPS data path is, so after we fetch this instruction, we want to know what we want to do with it. So the second part is decode. And remember, this is all happening in the same clock cycles, since we are discussing single cycle. So decode is examine the instruction and extract all registers and control lines. So if we have an instruction like add $S0, $S1, $S2, so what we mean by decode is, okay, knowing we need to figure out that we need to add registers involved are S1, S2, and S3, and 3 control lines. And we will build the control lines as we go with all different stages of the MIPS processor. So let me start again. So we have here the PC. Okay, we have a clock here. This is the only element with the clock, and this is the program memory. Okay, this is add. So we said we're gonna add, let me put it here, add $S0, $S1, $S2. I need probably to increase it more. And here we have the adder that adds 4, since it is byte addressable. So if we look at add S0, S1, S2, so the first thing we do is just write it in binary. So we know we have the opcode, which is 2, 3, 4, 5, 6 zeros. Then we have RS, this is RS, RT, and RD. So remember, this is an R format instruction. Okay, so here we have S1, which is going to be, if I look at my MIPS datasheet, I know that S1 is actually 17, S0 is 16, S1 is 17. So I write 1, 2, 3, 4. And then S2, which is 18. Okay. and I have S0 which is 16. Okay, then I have the shamped which will be 5 zeros. Then the function for the add will be 20 hex, which is 1 0 and 1 2 3 4. So this is the add in binary. Now from this instruction, and let's written in binary, this is a 32-bit instruction register. So of course this is the opcode. This will go into something called a control unit or CU, and from the control unit I will have all my control lines. The role of the control line is to control what will happen in the data path. So we're gonna leave it floating like this. So the second part is the registers that we are using. So of course here we're gonna introduce the register file. So this is the register file. Remember I have RS, RT, RD, data, and we have the two values that are coming from RS and RT. So of course here I need to wire those together. So I know that this is RS and this is RT and this is RD. Okay, so from here when I execute add and we decode this instruction, we have here S1, S2 and S3, S0. So S1 17 will come from here, so and it will fetch the content of S1 and the content of S2. So this is actually what we mean by decoding. So this is the fetch part and this is the decode. One of the control lines I'm going to talk about is called register write. So this is register write. So what register write does, if it's equal to 1, it allows write to the register file. If it's 0, we don't accidentally write to it, so we need a control line to specify if we need to write to the register file or not. So let me write this. Register write control line that allows writes to the register file. That is register write equal 1. So this means when register write equal 1, I can write to register file. When it's equal to 0, write is disabled. So where does this register write is connected? So I'm gonna like a dot here. So this is the first control line. So these two are connected. I'm not gonna connect them, so I will not mess the figure. So once add is fed to the opcode of add is fed in the control unit, the register write will be set directly to 1 in this case. This means I'm gonna allow the write. Okay, so this is the decode part of the instruction. The third step is actually we're gonna go ahead and execute the instruction. Now that we know we have an add, we have found the registers we're gonna use and their content. Let's say this 5 plus 6. So let's say here we have inside the register file we have 5 and 6. So what happens here, this will be 5 and this will be 6. So what we want to do is we're going to add 5 and 6 and then place the result in as 0 to be 11. Now, so after decode we have execution. So third step is execution. So now execution is actually using the ALU to do our job. So in the case of add, we just need to add those two numbers together. So make use of the ALU to perform desired operation. So in this case, I need to add the ALU. So here, let me draw it one last time and draw it fast. We have this, the fetch part. Drawing it over and over again just makes you understand it more and remember it more. So we have add. I'm not gonna draw the content now, but you get the understanding of it. So we have the register file here, and we have rs, rt, and rd, and we have the data here and the content of rs and rt, and we said that this will be equal to 5 in our example and this will be equal to 6. Remember, these are all 32 bits. So now, so this is the fetch, this is the decode. Remember, here we have the control lines, and this is the register write. So here I need to add the new part, which is the ALU. So I draw the ALU like this. So this is the ALU. This is 32 bits. And somewhere I'm going to tell him, okay, do additions. So this is ALU control. So I need to tell it somehow add. We're going to discuss this later. And then we have the result. This result should be fed where? To the data part. So I have 5 plus 6, I have 11. So 11 will be fed here, and I will save 11 in as 0. Okay, so this is the computational part. So in a sense, the add instruction is fully completed. We fetch the add, we then use the register file to fetch S1 and S2, and then we're gonna save this in S0. So this is S0, this is S2, and this is S1. So and then the value 11 is saved here. The addresses goes in RS and RT to generate 5 and 6, which are found inside the register file, and then we add them and we go all over here. So you might notice that, of course, the data path is still missing some parts, the memory. This part is actually called the write back. So write back, which I'm going to call it step 5, because we're still missing a step in memory operations. So there's a step missing here that I will add it later on, and you'll understand why I put the step 5. Writing result back to register file. Now for our next example, let's say we want to implement an I format instruction. So for this example, I'm taking add I $S0 $S1 0x0a. So as you might notice in the previous example with the add, we just have a R format layout. Remember, this is a 32-bit register that I take specific parts of it. For example, here the opcode will be from, this is the opcode, the first 6 bits, this is 6 bits, and then we have RS, which is going to be 5 bits, RT will be 5 bits, and RD also will be 5 bits. The data, of course, will be outputted from the ALU. This is 32 bits, and the outputs of the register file are also 32 bits. Now, what I want to say is this division is just logical, it's not physical. So the register is not actually divided into 6 bits, 5 bits, 5 bits, 5 bits, and here's the shunt. We're not using it right now. And the function will play a role with the ALU control to choose if you want to add or subtract or do any of these operations, which I'm going to discuss. So this function will control the ALU operations. However, now I have a different format. I have an I format instruction, which is add I. So the same register, I'm gonna write it in a different color. It's actually in this place. So if I write it like this, the opcode of add I opcode will be opcode. If I look at the data sheet, it's going to be 8 hex. So this means I have 0, 0, 1, 0, 0, 0. And the RS, this is the RS, is going to be S1, which is 17. Then RT, this is the destination. Remember, what add I does is register file of S0 is equal register file of S1 plus immediate, which is in this case 0x0a. So this is RS. RT will be S0, which is this is going to be 16. This is 16. This is 17 as address. This is the address. Alright, so now RD and champ and function does not exist. We just have 16 bits, and these 16 bits, this is going to be 16 bits. This is going to be A, so I write 0. Okay, this is first 8 bits, and then 1, 2, 3, 4, 2, 3, 4. So this is the 16 bits, which is a total of function, champ, and RD. Those replace this. Now, if I look at the operation of adding the values, so first I notice that the destination now is RT. It's not RD. And we know that in the previous example, RD was wired to the destination. This register is where the destination address lies. So in order to choose between RD and RT, which is R format and I format, I add here a multiplexer. Okay, and put this line which chooses now between RT and RD. Of course, so this is I format coming for I, and this is for R format. So if I want to choose R format, which I have to, let's say this is 0 and 1. So if I want to write the multiplexer here, just to show it. So we have 0, 1. This is RT, and this is RD. And this control line, this register is controlled by something called register destination. So this is the second control line, register destination. So if register destination is 0, I will choose the I format. If it's 1, I will choose the R format. And this way we are modifying our data path to support both R format and I format. So this is why we add this multiplexer. So now we solved the fact that I format uses RT and R format uses RD. We just add a multiplexer and we choose between the two using register destination, this control line. Now, what ADDI does, it adds the content of S1. So this is the content of S1, RS. So we have this. Now we have the immediate. There's the problem here because this is a 32-bit adder and this is just 16 bits. And this can be positive or negative. So what shall we do? We actually need to extend this to be 32, okay, and extend it using a sign extender, which means it will keep the sign. So this 16 bits, okay, is going into a sign extender, and we have here 32 bits. So here comes 16, and what outputs is 32 bits. Now this should be added. We only have one ALU, so of course we need to add another multiplexer, 0 and 1, and this now we can actually, this is 1, so this will go here, and this is the R format. So this is the R format addition and this is the I format addition from the immediate. And the control line that chooses this is called ALU source. So this is ALU source. So if ALU source is 0, then I'm passing the R format, which is RT. So this is the content of RT and this is the content of RS. So if this is 0, I pass the content of RT. If this is 1, I'm gonna pass from 0 till 15. This is bit 0 and this is bit 15. So I'm gonna pass this through a sign extender, which is going to transform the 16 bits into 32. So in this case, I'm gonna add just 16 zeros, and I have 0x, many zeros and A, and then this will be added, and I'm going to add those, and here I have no change because whether the addition comes from an R format or an I format is going to be from the output of the ALU into the data field of the register file. So you see now I just added two control lines, which is register destination, chooses where should I place my data, whether the source, the destination will be RT or RD, and another multiplexer here to choose between the content of RT in case of an addition, normal addition, or a sign extended immediate in case of an ADDI instruction. And for now the ADDI is fully done. Remember that this is all happening in a single cycle, and this is the clock that is controlling the execution of the whole instruction. The next step will be discussing now load and store instructions, which will be in the next lecture.